Swayam Prabha. Digital India. Educated India.
Good afternoon everyone, and today we will start with module 5, that is principles of texture measurements by X-ray diffraction. This lecture is lecture number 22, where we will try to understand macrotexture and microtexture measurements. So, the concepts that will be covered in this lecture is microtexture and macrotexture, different methods of texture measurements, diffraction and interaction of radiation with the polycrystalline material, which is matter. So, you see, what is macrotexture? Macrotexture is usually called bulk texture or global texture, and it displays a complete information about the distribution of orientation. So, it displays the complete distribution of orientation in space for a particular polycrystalline material which has been processed by some method, right, say solidification or deformation or any other method. So, the information that is obtained is usually represented in terms of pole figure or in terms of inverse pole figure, and we have already seen that inverse pole figure is usually used for axial texture measurements. The 3-dimensional orientation space, that is Euler space, consisting of Euler angles phi 1, phi 2, is also utilized in form of orientation distribution function, that is ODF, to to show this texture or orientation information. Microtexture on the other hand gives information about the local texture. Now, what is the difference between the local texture and a bulk texture? Local texture is basically localized variation in the orientation of the material, in the texture of the material, and this texture representation can be given in terms of a graphical representation, okay, like the one shown in this colored micrograph below. As we have shown this in previous lectures, that these colored micrograph is basically not a random colored micrograph, but it is a computer generated microstructure which gives the information of the orientation stereology. Now, these different colors of these different grains present in this microstructure shows different orientation, and this is given by this triangular color code. So, this is an example of an hexagonal close packed material, that is alpha titanium, which is a single phase and kind of a pure, commercially pure titanium. So, you can see that this material has a rolling direction vertical, a transverse direction which is horizontal, and in the plane of paper it has a rolling plane, that is perpendicular to the plane of a paper, it is ND, normal direction. You can see that various grains have been represented by different colors, and different colors represents the orientation of that particular grain in this microstructure. So, if it is red, that means this grain has an orientation 0001. When it is green, that means this grain has an orientation of 1 1 2 bar 0, whereas the blue grains have orientation near to 1 0 1 bar 0. So, this microstructure is a quantitative microstructure which is obtained by EBSD technique, and you see that when you talk about macrotexture, macrotexture as we know that it is measured mainly by X-ray diffraction or Newton diffraction methods. We will come to know in details in the later lectures that why these methods are used for macrotexture, and in case of microtexture, as I said, electron diffraction methods like electron backscatter diffraction in a scanning electron microscope, that is SEM EBSD, or orientation imaging microscopy in a transmission electron microscope, that is OIM in TEM, is basically used to obtain this kind of microstructure, and this kind of microstructure is basically known as inverse pole figure map and is mapped by a triangular inverse pole figure showing different color shades representing the orientation of the material. Now, you see that if we look into another specialized technique, this technique is basically synchrotron X-ray diffraction method, and this is a specialized technique where the X-ray radiation is obtained from a cyclotron measurement in say for example utilizing a beam line, so that a very low wavelength parallel thin X-ray beams could be obtained, and such X-ray beams have a very high penetration depth as well as very high spatial resolution. So, they become very specialized to obtain both microtexture and macrotexture information depending upon the equipment that we are using. So, microtexture depiction. Now, you see the same inverse pole figure map, that is the quantified orientation map microstructure obtained from a EBSD method using a field emission gun scanning electron microscope is shown here, and this is the microstructure of pure titanium. As I said, you can see that when we observe this microstructure, we can not only observe the orientation or the texture of this whole part of the sample, but we can observe the texture even in individual grains. So, if you look at this green grain, which is nomenclated as 1, what we can see is that the orientation of this grain is something like this with respect to the RD, ND and TD. Now, you see that this orientation is represented in terms of unit cells, and this unit cell, hexagonal unit cell, can be obtained by using this EBSD method. Like that, you see, we can observe the this twin that has formed. I know that it is a twin which has formed in the grain 1, and we have nomenclated it as 2, and you can see that the unit cell is sufficiently different from the grain 1. Now, you can see like that we can map grain 3, 4, 5, 6, and we can show that all of these have different orientations of the unit cell with respect to the sample reference directions, important sample reference direction, which in this case is RD, TD and ND. Now, therefore, each of these grains are being shown with respect to a different color code with respect to this inverse pole figure color code map. Now, you see that not only the information of the orientation of each grain is present in this scan, but it also contains the information of each pixel present in the material. It can give the information of, you see, if we draw a line in this in this grain number 10, and we can see that there is lenticular type of structure, which I am saying that these are kind of twins. And see, in case of titanium, extension twins usually develop, also contraction twins forms, but this is a case of the extension twin, and this extension twin usually has a axis angle pair, and that axis is usually 112 bar 0 and the angle is nearly 85 degrees. So, if we draw a point to point misorientation map, and you see that at these 2 points the misorientation reaches a peak which is near to 85 degrees, and you see we can also find out the length, means the thickness of the twins. So, you see that not only we can get the orientation of the material or the orientation of each grain or each positions of the pixel, but also we can calculate the difference in orientation, the mismatch of orientation between two adjacent grains or in between if there is a twin present, and we can show that okay, the angle, the grain boundary angle, the misorientation angle of the grain boundary is 85 degree in this case, and this twin is nearly say 4 to 7 micrometer thick, that means 5 micrometer, nearly roughly thick, right. Now, not only this, as I said that the twin boundary is a axis angle pair, right. So, we can obtain the misorientation angle distribution fraction for the entire microstructure, you see. And you see that in this case the fraction of certain misorientation angle is given in the y axis and the degree of the misorientation angle is given in the x axis. Usually in case of quantitative microscopies like electron backscatter diffraction techniques, the misorientation angles greater than equal to 15 degrees are considered to be high angle grain boundaries, and that is they are considered to be grain boundaries, right. Those angles which are lower than 15 degrees are basically known as low angle grain boundaries or low angle boundaries, and they corresponds to mainly geometrically necessary boundaries present in the material. Now, you see that when we look into this misorientation angle distribution fraction, we observe that there is a peak at around 85 degrees, and as I have said that twins that usually form in titanium are extension twins, and they have a boundary, grain boundary or the twin boundary having an 85 degree misorientation about the 112 bar 0. So, in order to see that why this kind of peak is observed in this material, if we look into this material here, this microstructure here, we can see that here is one twin, there is another twin, there are few twins here, intersecting twins are present, this is one twin, here are another twins, intersecting twins. So, in the whole microstructure you see there are a lot of twins present, and therefore the boundaries of these twins could be observed more largely. So, their fractions will be more. So, if we look into this 85 degree boundary in terms of angular inverse pole figure, an angular inverse pole figure like this one, and we will see a high intensity at a certain axis, right. This high intensity at a certain axis for this case comes at 112 bar 0. So, there is a lot of 112 bar 0 axis having 85 degree in angular and axis and angle relationship. So, it is a kind of a special boundary usually called as a coincident site lattice boundary, but we will come to that in the later section of the course. And if we look into this, I have enlarged it, we can see that even the axis angle pairs could be identified using the microtexture process. But on the other hand, macrotexture does not give such in-depth information. Rather, macrotexture gives the information from the bulk sample and is basically a complete property of the sample, a representative information from the sample. Whereas microtexture though give depth information of the sample, the information is obtained from a very small area of the sample and therefore may not be the complete representation or complete property of the sample. But both this method together we can utilize to obtain information and for obtain information of any product, to change processes in industry, or to carry out research activity to understand more about different kinds of deformation behavior or any other processes that can that happens in polycrystalline metals and alloys and are important for engineering application purposes, technological development purposes. So, the methods of texture measurements, we found out that macrotexture measurements are done by X-ray diffraction methods and neutron diffraction method. X-ray diffraction method, you see, measures average texture of the surface. Its penetration depth is low, but its penetration depth could be about 10 micrometer. So, it can be considered to be utilizable for macrotexture measurement. Neutron diffraction method, you see, neutron radiations are very difficult to obtain. Usually they are obtained in a what you call nuclear reactor, where neutrons are produced and then they are basically utilized to in the beam line of the nuclear reactor to form to obtain texture information when it is radiated on a surface, so that the neutron diffraction could be obtained. Now, you see, the neutrons actually penetration depth is very high and therefore about centimeter. So, it can penetrate more than a centimeter inside the material, and we will talk about this in detail in the coming slides and in the next lecture. But you see, the information obtained from the neutron diffraction is much more bulkier than the one which is obtained from the X-ray diffraction method. Usually, the information obtained from the X-ray diffraction and the neutron diffraction are not that different, but in certain specialized case, when X-ray diffraction may not be able to give the information that is required, or because of the heterogeneity in the texture present in the material, neutron diffraction may be utilized in some specialized cases. So, the third is the synchrotron X-ray method. Now, you see, as I said, that synchrotron is a specialized beam and it is an X-ray beam, and it is usually known as short wavelength X-ray beam. Now, you see, the intensity of the synchrotron X-ray is very high. Its wavelength lambda is lower than the wavelength lambda of X-ray, normal X-rays, and X-rays are actually divergent beams, but as the intensity of the synchrotron X-rays increases, the divergence of that high intensified short wavelength X-ray beam, synchrotron beam, can be reduced and parallel beams can be obtained. And under such situation, high intensity very thin beams can be obtained, and because of the reduction in the wavelength, its penetration depth increases to few millimeters, and therefore one can utilize this powerful specialized radiation in order to carry out both macrotexture and microtexture. The fourth method, as I said, is electron diffraction method. One can use SEM EBSD or one can use TEM OIM. Now, SEM EBSD is much easier to utilize because preparation of sample of a TEM for orientation imaging microscopy is extremely difficult as compared to the EBSD microstructure preparation, even though EBSD microstructure preparation is also considered sometimes difficult for some materials such as magnesium and titanium, etc. In case of nanostructure grains, in many materials. So, you see these methods give local texture as said in the previous slide, and it has a lower penetration depth. The penetration depth depends upon the atomic number of the material being irradiated, but on an average it is said that the penetration depth is usually less than 1 micrometer. So, it gives the complete information as I said in the last slides. Apart from this, ultrasonic methods can be used to give qualitative information of the changes in the texture, in particularly used in industries. See, most of the time ultrasonic methods are used to detect if there are any flaws or fractures in the material coming out of the production line. But if you see that if a certain texture is desirable, the ultrasonic intensity change that occurs because of that particular texture also changes if the orientation changes. So, if a certain orientation or a texture is desirable, then the industry connects the final product or observes the final product under an ultrasonic method technology to see the changes in the intensity of the ultrasonic waves, leading to see whether the material that has been produced is suitable for application or not. On the other hand, even using optical microscopy, one can get a slight understanding that whether the material is textured or not. So, you see plane polarized light if you use in an optical microscope can deflect the light in such a way that in a grain in several grains it can produce different shades of color, indicating that the crystal structure on the plane is slightly different and thus indicating the change in the texture. But this is a very qualitative information and it only gives a very limited information about the texture of the material. So, if we look more closely into the diffraction of these radiations which are electromagnetic radiations and their interaction with the matter, we can see that the radiations initially when it falls on the atom, basically it scatters in all the direction. Now, when it scatters in all the direction, it is interacting, we are considering only one atom. But when there is a periodic arrangement of atom in space, the scattering of these electromagnetic radiation from one atom in all the direction, the intensity of the scattering may not come out fully from all the direction, but it may come up from certain direction, and these direction is basically following the Bragg's law and it is following the structure factor relationship because of the periodic arrangements of atom in that particular polycrystalline material. So, diffraction techniques are basically reinforced scattering. We have already talked about this in much earlier in this lecture series. So, using these method we can obtain crystallographic arrangement, and most importantly for this course we can obtain the orientation of the material with respect to any fixed sample, important sample reference directions or reference axes. So, you see that in order for the material in order for the radiation to get diffracted via a periodic arrangement of atoms in a polycrystalline material, the lattice spacing of these atoms or the bases will have to be slightly larger than the wavelength of the incident radiation, right. So, that is how if the wavelength of the incident radiation is much smaller than the lattice spacing, then only the diffraction will initiate in this lattice planes. So, let us see the properties of radiations to be considered for texture measurements by diffraction. You see here we have shown the wavelength of the X-ray is in a range of 0.05 to 0.3 nanometer. Its energy in electron volts is 10 to the power 4. It has no charge, no rest mass, and it has a penetration depth or absorption length of 0.01 to 1 millimeter. Now, why I have written 1 millimeter? Because I have considered short wavelengths and synchrotron wavelength, synchrotron X-ray radiation with a lower wavelength. So, you see that interaction of X-rays with the matter basically decides the penetration depth and the absorption. Neutrons, you see, have the same wavelength, its energy is also less, its charge is 0, it has a higher rest mass. X-ray does not have any rest mass, but it has 1.67 into 10 to the power minus 24 grams rest mass per neutron, and so its penetration depth is much higher, about, you see, 10 millimeter to 100 millimeter, or sometimes more for some materials. Now, why is this? We will come to this in a later stage, but still you see that neutron diffraction, it has no charge and it interacts only with the nucleus of the material, and therefore it has a lot of space to go and have a large penetration depth without any absorption, just by logic, you know. So, let us go to the electrons. Now, electrons have a very low wavelength and it has, you know, energy, you know, much higher even than that of the X-ray. It has, you know, charge, a negative charge, and it has a rest mass, though lower than the neutron. But because of its interaction with, you know, different shell electrons and also the nucleus of the material, its penetration depth is very low, 10 to the power minus 3. Here we have also given the, you know, the wavelength of light. It is of the order of 400 to 700 nanometers, which is much higher than the, you know, lattice spacing of any periodic lattice arrangement of any metals or atoms, and therefore you see that even though it does not have, it could not penetrate the atom, it cannot give any diffraction from any polycrystalline material. So, light, because of the higher wavelength, much more larger than the lattice spacing, could not give any diffraction. So, if we look deeply into these radiations, you see that the absorption length and penetration depth of these radiations depends upon the way these radiations basically, you know, interact with the matter. So, you see electrons, it interacts with nuclei and the shell electrons, and so its penetration depth is very low, and therefore it gives only microtexture information. Electrons can be, you know, deflected using condenser coils, and thereby thin beam of electron can produce, and therefore it can give in-depth information in that microtexture regime. X-rays, on the other hand, interacts with shell electrons. It does not have any charge, it does not have any mass, so it can go deeper, but still, because it is interacting with the shell electron, its absorption is high, and therefore it could go up to few micrometer level only, and therefore it can give macrotexture information. Neutrons interact with nuclei and it can penetrate deeper. It has a very low absorption coefficient, and we usually call it linear absorption coefficient or mass absorption coefficient, and therefore it gives information of the macrotexture, more deeper information of the microtexture, because it can penetrate up to few centimeters. Synchrotron X-ray, on the other hand, interacts same way as the normal X-ray with the shell electrons, but it has a lower wavelength, and this leads to a higher penetration depth, than few tens of micrometer to millimeter level, and therefore can give a better information of the macrotexture. On the other hand, it can be produced like a thin beam, as I said earlier, therefore can be used for microtexture either. So, X-rays are basically electromagnetic radiations which diffracts mainly by elastic scattering of the incident waves at the atom in case of any sample material. But if we look into the electron beam or the neutron beam, they are basically particles which are travelling at a higher speed, so that it becomes a particle beam, and therefore these particles exhibit certain wavelength and they look like a wave of radiation, and therefore they exhibit certain wavelength. And if we look into the de Broglie's relationship, which is given by lambda equal to h by mv, where h is the Planck's constant, lambda is the wavelength, m is the mass, v is the velocity, and if E is the kinetic energy of the material, that is equal to half mv square, then the lambda can be calculated to be equal to h, that is Planck's constant, divided by root over 2 times mass into kinetic energy. So, if we calculate, we can obtain the lambda from this, and you see that thus the electron and the neutron basically behaves like a wave, and so even though it is a particle, using the de Broglie's relationship. So, as diffraction is reinforced scattering and it produces because of the presence of the periodic structure of the material which is in which it is interacting, it basically follows the Huygens-Fresnel principles, which states that every point on the wave front can be considered as a source of wavelength. So, each point of the new waveform front can be considered as a source of wavelets that spread out in the forward direction. It spread out in the forward direction at the same speed as the initial source wave. That is all. So, what we came to know from this lecture? We came to know that most of the scattered radiation is scattered in all the direction, therefore they are in out of phase. So, this leads to mainly annihilation of the the reflected intensity to mostly 0. So, only at specific angles, which is following the Bragg's law and the structure factor principle, the wave fronts are actually in phase, and these are the angles at which diffractions are basically observed. So, what are the conditions of diffraction? To summarize, it is that radiation has to be monochromatic, it cannot be polychromatic, it should have a specific wavelength, that means. Secondly, the lambda must be of the same or a smaller size order than the periodic lattice arrangement of that particular material in question. And third, and the most important thing, is the arrangement of the atom has to be in order, right? It has to be a crystalline material. So, what can be concluded? It can be concluded that macrotexture or bulk texture or global texture gives the complete information of the texture of the sample. That means it can give the property of that sample. Okay. Microtexture basically gives the localized information of the texture, and it can be shown in terms of a graphical representation like the inverse pole figure map that we discussed in the initial slides, and this gives the information of the microtexture. It may not be the texture representation for the whole sample. The information is about microtexture or macrotexture. It depends upon the radiation's absorption length, okay, which is basically mass absorption coefficient. We will talk about this in the next lecture, and it decides the penetration depth. Global texture can be measured by X-ray diffraction and neutron diffraction. Microtexture can be measured by electron diffraction because it has high spatial resolution and it has very low wavelength. Synchrotron X-rays have high intensities and therefore can be converted into parallel beams. It will then have very high spatial resolution. It will have a lower wavelength as compared to the X-ray, therefore it will have a lower absorption coefficient and therefore a higher penetration depth, and can be utilized for micro and macro texture measurements both. Thank you very much.